Okay, I've decided that we're going to actually attack this question a little more deeply. I was thinking I could get away with sort of a quick pass to sort of explain how bras and kets in quantum mechanics correspond to vectors and dual vectors, and that's not too hard to get by. The problem is that you very quickly, it's more than just this, because we've studied vectors and dual vectors in a very specific way. We identified a vector space that we would say contained all these vectors in it, say v1, v2, and of course it's an infinite set, and it has there's usually a bin of scalars, which we were using the real numbers, but could, for quantum mechanics, be the complex numbers. And then we talked a little bit about vector fields, right, where we're actually putting a vector space at every particular point in space-time, and then the components of any given vector would be functions of the space-time. So if, for example, I had a vector v, then it might have component c, function of space-time, basis vector E1 plus C, I guess that would be C1 plus C2, function of space-time, basis vector E2, and I guess we would use our Einstein sum notation and we'd do this, right? And so we had a vector field, so we had one vector space at every point in space-time. Quantum mechanics doesn't do that, and to address that point is a little more than hand-waving. We have to point out that quantum mechanics, there's only one vector space. There's only one vector space V that you're dealing with, and it contains all of the state vectors of the system. You no longer have this one vector space at every point in space-time and with some kind of beautiful coordinate system, and all the vectors are going to be represented by differential operators. That's gone in quantum mechanics. Quantum mechanics, you have one vector space. And then the other problem is that one vector space, no matter how you slice it, has a fundamental distinction from all of the vector spaces we deal with in GR. And that's that it is infinite dimensional. Right? So, whereas in GR you have an infinite number of vector spaces, in quantum mechanics, you have one vector space with infinite dimensionality, and that's not meant to be some kind of equivalence. It's not like that's the same problem looked at from a different angle. It's a totally different situation, right? So to really understand how vector spaces are used in quantum mechanics, I can't make a very credible one-to-one correspondence where I put quantum mechanics over here and general relativity over here. If I did, let's try it and see what would happen. You can get a certain far, right? You can say, okay, in GR you have a vector space V that is spanned by 4 basis vectors. In quantum mechanics, you have, we'll say, vector space script EV, but it's got an infinite basis. And that infinity can be countable or uncountable, right? So that's another problem. So that's one distinction. So I'll just write down infinite basis and then finite basis. Right, so that's one thing. The other thing is this is a real vector space and this is a complex vector space. And I'll remind you, the complex vector space in the nature of being complex has nothing to do with the actual vectors themselves. It has to do with the bin of scalars, right? The scalars are complex numbers in quantum mechanics, and the scalars are real numbers in general relativity. Now, they are both, interestingly enough, they're both inner product spaces, right? So I can say that they're both inner product spaces, meaning they both have an inner product. Out here, as a practical matter, we deal with the metric as the object, the mathematical object that carries around the inner product. And you'll remember we talked a lot about the equivalency of the metric. The metric defines an inner product. The inner product on the vector spaces defines a metric. And again, this is also complicated by the fact that the metric itself is a function of space-time, because it is a tensor that lives at every point in space-time that handles the vector space at each individual point in space-time. So inner product is handled through a metric that's continuous on space-time. That's a metric field, right? So this would be a metric, which is actually a tensor field, right? So in quantum mechanics, the metric is handled very, very differently. The metric is handled entirely through the dual space, right? So the dual space is defined in quantum mechanics, and the action of the dual space and basically what happens is a one-to-one correspondence is established between the dual space and the vector space V. And once you've established a one-to-one correspondence between the dual space and V, you basically selected that mapping. Well, if you had an inner product on V, it would force a mapping between V and the dual space, which is V star, right? We talked about this in the What is a Tensor lecture. So in quantum mechanics, they basically kind of go the other way around. They establish the correspondence between the dual space and V, and they let that correspondence establish the inner product, right? All of these things are ultimately equivalent, but the emphasis is so different that it's very hard to make the connection. But in general relativity, any arbitrary vector could be expressed as, say, AI, EI, right, with the summation, or I guess we would use A mu, E mu in 4 dimensions, usually the Greek letters. And we use this Einstein sum convention. You never use the Einstein sum convention, but here you established an arbitrary ket, which is a vector in V, right? All kets are elements of the vector space. An arbitrary ket is, and you always use the summation convention over I of Ci, and then you have these basis kets, phi n I. I called the basis kets phi n here, so I should call the arbitrary ket something different, like, say, psi. So there's no Einstein sum convention, and the problem is that this sum is infinite, right? And you know, that's not too big of a problem, but it could also be, this here it's infinite and countable, but it could also be infinite and uncountable. So it'd be C, I guess we would use a little k typically. No, what would we do? We'd use C as a function of some index variable k, a continuous function of an index variable, and then it's phi k, and then it's dk, right? These two things are the different ways of expressing a vector an arbitrary vector in the vector space of quantum mechanics, where the vector space of all state vectors. But notice that in this case you have an uncountable number of basis vectors, so you have to take an integral. So you have what's called a spectral function here, as opposed to a discrete spectrum in this case. And these are not the same circumstance. One of the huge problems, though, if you're going to pretend to want to know the foundations of quantum mechanics, is this notion of an infinite basis is a very tricky idea, and it has to be thought about carefully. It's fine for us to advance through quantum mechanics under the assumption that if I have an operator, that operator has an eigen equation. Say I have the operator operating on a wave function. I better stick with the wave function stuff from the last lecture because I haven't really introduced these guys deeply. But if you have the operator acting on a wave function, you get some eigenvalue. There's an eigenvalue equation, right? There's a certain collection of eigenvalues such that the operator returns a constant times the same eigenvector. There's a certain collection of eigenvectors, in this case eigenfunctions. In wave mechanics you call them eigenfunctions, and the operator will return an eigenvalue and the eigenfunction. And then it's okay to, as a young student of quantum mechanics, to say, well, we're going to accept the fact that the set of all these eigenfunctions spans the set of all possible states of the system. So that means that any state of the system or any wave function can always be, any wave function of the system can always be expressed as the sum of these wave functions times some I, Ci over I. And there will be an infinite number of them, usually. I mean, all the interesting problems, there's an infinite number of them. And in the problems that involve where this Hamiltonian leads to a continuous spectrum, then psi is going to be given by this integral ck phi k dk, where now we have a spectral function. So you can accept this as true. The eigenstates of Hermitian operators span the space, and any function can be modeled in this way or this way. If you accept that, then that's all you need to know about the foundations of quantum mechanics. You don't need to know any more. The question is do we want to spend the time studying these vector spaces, these infinite dimensional vector spaces, enough to see why these statements might be true or might be acceptable? And, I was going to attack this and say, no, why bother? But actually, I think it's worth bothering. I mean, the whole point of these lecture series is to make people more comfortable with these concepts, not hand wave. I mean, that was sort of the motivation of starting a lot of this with with general relativity, was the idea was to make people comfortable with the idea of vectors by digging in really deep. So if you've studied quantum mechanics and you've solved the harmonic oscillator in 1 and 3 dimensions, and I don't think I ever solved it in 2 dimensions, but 1 and 3 dimensions. If you've solved the infinite square well, the finite square well, the barrier penetration idea, if you've done all of those, the WKB approximation, the hydrogen atom, if you've done all that work, and you've kind of done it, you've probably done it resting on this sense that, what's going on with the so-called Hilbert space? Because that's what this is, right? That's what this is. This is a Hilbert space. And ultimately, did you ever think deeply about what the Hilbert space was and how is it relevant to quantum mechanics? And you probably have not. So what we're going to do is we're actually going to penetrate this idea a bit. I've decided I'm not just going to hand wave through it and make the connection between things. I'm actually going to talk about the Hilbert space and get it so that this idea is is comfortable enough that you can put a check in the box and move on. Of course, it's going to be a series of lectures, right? So you can take them as far as you wish and develop them as much as you like. But that's the plan, and let's begin. All right, to understand what we're talking about today, the prerequisites, the prereq is you have to know quantum mechanics, right? This is not a course in quantum mechanics. If you've learned quantum mechanics through wave mechanics, which is pretty typical, then you'll be fine. As long as you know quantum mechanics enough to, and presumably you've solved all the basic problems. The simple harmonic oscillator is one. I gave a few examples a moment ago. Simple harmonic oscillator. The hydrogen atom is probably the most important. Hydrogen atom. Scattering is cool. Scattering theory, WKB approximation, all of the basic stuff. Presumably you've had a course in that, or you've attacked that one way or another. And because of this, I think you understand how to interpret the wave function and all of those things. The other thing that will be necessary is elementary topology. Of the type that I did in What is a Manifold? So what is manifold? Around the first 10 lectures or so basically covers some of the elementary topology. Now we're going to actually recast some of that elementary topology the way we did it in this lecture in the form of pure classical analysis. analysis, which usually means defining open sets in terms of sequences. And we'll probably do that stuff on the fly, but it is basically it's pretty much a sophomore course if you're a math major, but it's a course you'll never see unless you're a math major, which is classical analysis. So we'll need to know that. You'll need to know linear algebra. Oh, and what is a tensor stuff, right? I'm going to lean on the what is a tensor material still, even though I've gone on and on about how making this connection is harder than I thought. The what is a tensor stuff is still solid. It's a solid place to start. You just have to back up to the beginning before we talked about vector and tensor fields, and then start again. And that's what we're going to do. So the what is a tensor, probably about the first, I'd say, I know, somewhere around the first 20 lectures or so. I know it's a lot of lectures, but now the issue is that in order to understand a Hilbert space, you've got to kind of proceed in a definite direction. You begin with sort of algebraic concepts. Algebraic concepts start. All right, and the algebraic concepts are the concepts of a vector space. In the language of pure math, they call it a linear space, but it's just a vector space as we know it. So the vector space is an algebraic construction, and so that's where we begin. We begin with a vector space. But we're not going to specify the dimensionality anymore. We're no longer going to say it's finite dimensional. We're certainly not going to say it's four-dimensional, right? So it's possibly infinitely dimensional vector spaces. In fact, we're going to talk about both finite and infinite dimensions, but we're going to talk about finite dimensional spaces more because we're going to discuss how proofs that make things obvious for finite dimensional spaces are unavailable for infinite dimensional spaces. Okay, so we'll start with the algebraic concept. Then we have to go to the topological concept, topological ideas. The topological ideas, we don't have, if you think about it, and now I'm leaning on this first prerequisite, by the way, when we studied our vector spaces in what is a tensor, when we studied these vector spaces, we never established a topology on the vector spaces. We never talked about the topological structure of a vector space. In the What is a Manifold series, we talked about the topological structure of sets in general. And we spent a lot of time about that. So we could talk about open sets and topologies and closed sets and topological invariants and homeomorphisms and diffeomorphisms in particular. So in order to get to diffeomorphisms, which is important when you talk about manifolds, you really had to go through topology. But at no point did we ever say, oh, if you've got a vector space, you have a topology on that vector space, which isn't true. There's no canonical topology for an arbitrary vector space. So in order to establish a topology on a vector space, you have to add some topological ideas. Well, in particular, what you need to add is you need to add at a minimum the idea of a norm, right? And a norm is one of these functions that take vectors and produce numbers. So a norm is something we've already sort of seen before. We've seen a norm that takes two different vectors. We've seen it, well, let's say, put it this way. We've seen a function that takes the inner product, took two vectors, right, and produced a real number. Or now we take two vectors in quantum mechanics and we'll produce a complex number, but regardless, it takes two vectors and produces a number. A norm only works with one vector. So you have a norm of one vector and you end up with a real number. Or, well, a real number. So this is a little bit more elementary than an inner product. And in fact, in the classical presentation of analysis, you start with, in your vector spaces are given something often called a metric, which is unrelated to the metric of general relativity. It's called a metric, but it's really, the idea is that it is a distance function. It's a distance function. and but even this is more than what a norm is. A norm is even less than that. So we'll have to talk about what a norm is. But ultimately, in order to create a topological idea, you have to have at least a norm. At least a norm. If you have an inner product, that's good too. But you need at least a norm. Then the topological ideas give way to analytical ideas. Analytical concepts. I'll alternate between ideas and concepts. And analysis usually has to do with the ideas of convergence. Convergence. And you already heard me say in the last lecture that the Hilbert space was a closed version of the was something that was closed under these Cauchy sequences. So in order to have Cauchy sequences that limit to something, you have to have an idea of convergence. In order to have convergence, of course, you need to have the topology. In order to have the topology, you have to have an underlying set, which is this algebraic vector space. So then with the analytical concepts, we create convergence. And then the last thing is geometry. And with geometry, that's where you need the inner product. Because the inner product essentially defines orthogonality. Orthogonality, right? So the inner product defines orthogonality. So with geometry, you finally have to add an inner product. And as you go down this list, right, we're pretty good here, so we're ready to go. This won't be too hard to add. This is where it's going to be hard. This idea of convergence, we're going to have to do some proofs that involve really well, basically analysis that most physicists are not very familiar with, but ultimately, in some sense, it all has to do with like epsilon delta proofs that you may have learned in calculus. Hopefully you did. And then when you finally get to the geometry, you get the inner product. Down here at the bottom is the Hilbert space, right? So a Hilbert space, it is a vector space that has this idea that has a topology established upon it, and that topology is derived from the norm, but that norm is derived from an inner product, right? And once so the Hilbert space has an inner product which gives it a norm, which establishes a topology, which allows you to define convergence. And once you have the convergence, you can establish what's the completeness of the Hilbert space. And then once you have the complete Hilbert space with the inner product and orthogonality, you can have geometry. Phew. So that's the dog we have to walk through all of these ideas in order to get to what I'm calling the foundation math of quantum mechanics. Now, understand, when I say I'm talking about the mathematical foundations of quantum mechanics, I'm really talking about getting to the bottom of this thing, right? Along the way, what do we have? This part here. If you have an algebraic space, you've got a pure vector space. If you have an algebraic space with a topology, then what you have is a normed vector space, right? And then if you have a topological space that's complete, meaning you use this norm and exploit it to include inside this algebraic space all of the limits that are possible, then you close the vector space. And by the way, you'll see that for finite dimensions, saying that you close the vector space is absurd. It's finite dimensions, all vector spaces are closed. In infinite dimensional spaces, that's not the case. So you have to add the closure to it. And if you do that, you end up with what they call Banach space. And then if you give your Banach space an inner product, you get a Hilbert space. All right. So we're going to try to go through this process. I don't know how long it'll take, but I think it's worth doing. All right. So that's a review of where we're going to go with this. The previous lecture, which I wanted to kind of disregard. I'm going to keep that. That is going to stand sort of a warm up, because those wave functions, those wave functions we talked about, are going to ultimately be the things that live in our Hilbert space, or in at least one representation of our Hilbert space. So having that review is still fine. All right. So the next time, what we're going to do is we're going to go through some of these early ideas about normed vector spaces.